Hello, and welcome to the last lecture of the semester. In this lecture, we'll be covering two topics that are generally described as modern physics, and modern physics in the sense that they've been developed in the last 120 years, specifically relativity and quantum mechanics. And those do relate to light, so in some way they are a capstone to how we've described light so far, describing light as first as a wave, then as a particle, a ray, back to a wave, and now we'll see two additional consequences of light that have been observed experimentally. Specifically, a lot of the effects known in special relativity come from the fact that the speed of light is always constant regardless of how fast you're moving. And so that's the theory of relativity is based on experimental evidence. It's not just a pure mathematical consequence, but it is a consequence that was observed experimentally, and so the laws of physics followed from experimental evidence. And what we'll cover specifically out of quantum mechanics, I'll discuss quantum mechanics and relativity conceptually. We really won't be getting into the hardcore mathematics of relativity and quantum mechanics simply because it would take too long to simply introduce the subjects mathematically. And so we'll emphasize the concepts behind relativity and quantum mechanics, but we'll also do some relatively straightforward calculations that get to the essence of the concepts there. So in quantum mechanics, we have particles, and specifically light, but it also applies to matter, particles of matter, but specifically we'll see it applied to particles of light, photons, how photons are described in such a way that encapsulates both their nature as a wave and a particle, specifically in the context of the photoelectric effect. So we'll really talk about one experiment, the photoelectric effect, and the consequences that has in regards to being able to understand light as both a particle and a wave. And so other than that, we'll really just cover these topics conceptually, do a number of calculations that involve equations that just kind of get to some of the core ideas, but don't really, we won't really unpack all of the complex mathematics simply because it would take too long at this point in the semester. So the first thing I'd like to talk about is relativity. So the principle of relativity is that if you're moving at a constant speed, the physics that you experience are the same physics, not only experientially but also mathematically. The physics that occurs is the same physics you would experience as if you were completely at rest. So whether or not you're completely at rest, or if you're moving at a very high speed, your physics will be exactly the same. And since they're exactly the same, in some ways there is no meaning to being absolutely at rest. We always, whenever we would think, are we moving or are we at rest, that definition has no meaning because your relative motion can only be measured with respect to something else. So even if even if our solar system is moving through the galaxy at 70% the speed of light, there's no way we would be able to experience that if we're in that reference frame of moving at a very high rate of speed. The physics will be the same as if we were absolutely at rest. And so being able to identify your reference frame as being truly zero velocity is impossible to do. You can never say that you are at zero velocity because relative to some other solar system or some other galaxy, you are moving relative to that frame of reference. And so there's no real ground level to be able to define a true absolute rest. We can only measure our state with respect to something else. But ultimately, the key kernel of physics there is that if you're moving at any speed, it could be the trivial case of your velocity equals zero, but no matter if you're moving at a constant velocity, your physics is identical to that if you were moving at zero velocity. So as long as you're moving at any constant velocity, the laws of physics always have to be the same. And we experience that. We're moving around the sun at 30 kilometers per second, so that's a pretty good clip. But we treat our actions here on Earth as if we're absolutely at rest, as if we're not even moving through space at all, and life still goes on. All the physics is the same. We can just treat the situation as if we were truly absolutely at rest, even though we're moving around the sun at 30 kilometers per second. Our experience of the physics, even if as long as we're moving at a constant velocity, is going to be the same as if we were moving at 0 kilometers per second relative to the sun. And so that principle is key to both special relativity and general relativity. And so I'll get into some of the differences between special and general relativity, because they are two different theories that cover two different things, but they are sort of lumped together under just the general umbrella theory of relativity. So the principle of relativity that I've mentioned, if you're moving at a constant velocity, your physics is going to be the same as if you're just completely at rest. One clip I can show you to illustrate that, if you're jumping up and down on a trampoline, the fact that the trampoline is moving at a constant velocity, you're still going to jump up and you're still going to rebound up and down off the trampoline. It's going to be the same as if you were just if the trampoline was at rest relative to the ground. It's moving relative to the ground. So again, any type of motion only has meaning if you're comparing it to something else. If you're comparing your motion to nothing else, trying to define a velocity has no meaning, and you might as well just assume that you're not moving at all. Even if you are moving very quickly, you can just assume that you're not moving at all, because the physics will be the same whether or not you're moving or not. So that's kind of the idea behind the principle. But this principle, it was found again experimentally in the Michelson-Morley experiment, which used interferometers, which I mentioned last time. That experiment showed that the speed of light sort of worked independently of our conventional view of relativity. So the reason why this works is because as you jump up and down on the trampoline, as the tractor underneath moves to the right, the person on the trampoline who's going up and down is also moving with the tractor. So as soon as he bounces off the trampoline, he's moving directly overhead the tractor that's moving underneath him. So obviously, if you don't have any air resistance effects or anything that would disturb his motion sideways, that keeps him in line with the tractor, he'll experience that trampoline as if he was just completely at rest. But the thing about light that was observed experimentally is, if instead of a person jumping up and down on this trampoline, if you had instead a light beam that was shot straight up out of this trampoline, light does not obey this classical interpretation of the principle of relativity. Light instead, if the light was bouncing up and down on the trampoline, or wouldn't be, if there was a mirror and light was bouncing back and forth on the trampoline, light is unaffected by the relative motion of the object from which it was emitted. So if you had a beam of light that rebounded off the trampoline, what you would find if the tractor underneath was moving at 99% the speed of light, or some ridiculously high rate of speed where these effects are actually observable, if that light, as soon as it left the trampoline, instead of staying directly instead of staying directly above the trampoline, light is unaffected by the velocity of the object from which it was emitted. So the light, instead of staying directly over the trampoline, would actually fall behind the trampoline, because the tractor and the trampoline would be moving with this sideways velocity underneath it, but the speed of light would be constant. It wouldn't be affected by the velocity of the object from which it was emitted. It would just shoot straight up, and it would not move sideways. Instead, the light would shoot straight up, and the tractor would move out underneath it. Again, for most everyday situations, we would never experience that, because the speed of light is so fast relative to the velocities that we experience, that these effects are never really observed in everyday life. And that's one reason why relativity in quantum mechanics is so complicated, because it's so abstract, in the sense that we never can actually experience those effects. That's also the reason why Physics 1 is generally better understood than Physics 2, because Physics 1, forces, motion, energy, momentum, are all things that we experience every day, whereas Physics 2, electricity and magnetism, although we are familiar with them, we're less familiar with those abstract consequences of physics. We're less familiar with them than forces and motion, and that continues on in relativity and quantum, where we are even less familiar with the effects of that. So this is an aspect of relativity that was shown to be true by various experiments, specifically the Michelson-Morley experiment, where an interferometer was used. And the idea there was, since the Earth is moving, the speed of light should be affected, because the Earth is moving, and the speed of light will be affected by the Earth's motion. But what was seen instead is that the speed of light is unaffected by the motion of the object which emits it. And so in the context of the Michelson interferometer, no interference effects were seen, indicating that the speed of light was constant, even though Earth was moving underneath it. And so that's the idea that I'm getting to here, is that classically, velocities, would add there, but if you applied this situation to light, what you would find is that the tractor would move out from underneath the light. The light would go straight up, but the light would not move sideways with the tractor, because the speed of light couldn't have that additional sideways velocity in addition to its upward speed of light velocity. And so the light would move up, and the tractor would move out underneath it. Another way to visualize that is here, which is found in one of the videos that I've linked in the lecture outline. Would headlights work at light speed? So, a very intriguing title. So in this setup, we have a rocket ship that's at rest, relative to a rocket ship that's moving at 99% the speed of light. And the rocket that's moving, it has its length dimension distorted. And so what that means is that if we're assuming that you're taking the perspective of a person who's in the rocket ship at rest, and if you observe the rocket ship that's moving at a very high rate of speed, what you'll observe is that the dimensions are distorted, and that is a result of the speed of light being constant, independent of the object's motion. And so, and we'll get into the mathematics of that distortion in just a minute. So right now I'm just trying to illustrate the constancy of the speed of light. So if you're at rest, so if we have a rocket ship at rest and another rocket ship moving at 99% the speed of light, they'll both turn on the light at the front of the rocket ship at the same time. Oh,
let's check out what's on the news
timing
today.
Other news, how socialism is actually cool, and how real moving ship.
All right, they're turning on their headlights at the same time. So the rocket ship that's stationary, the light will shoot out, and it will shoot out at the speed of light. But the rocket ship that's moving at 99% of the speed of light, it turns its headlight on at the same time, right when it passes that front point of the rocket ship at rest. And so the speed of light being constant means that that the light that was emitted from the rocket ship at rest travels a certain distance, and the light emitted from the rocket ship that's moving, it actually has traveled the same distance. You can see, if you were to draw an imaginary vertical line, that light has been unaffected by the underlying motion of the object that emitted it. Even though the rocket ship that was moving at 99% the speed of light was moving extremely fast and it emitted its light was emitted at the same speed, and so it covers the same amount of distance. As you can see, the beam from the headlight matches up and matches up. So the speed of light, that's an illustration of how the speed of light is constant and it's independent of the motion of the object that emitted it.
Exactly what the crew of the stationary ship sees. Light beams rapidly.
So you can see that you know, the spaceship that was moving that emitted the light is actually catching up to the light which it emitted.
Their headlights at the speed of light, just as
another effect is that the wavelength of light is Doppler shifted. So just in the same way that you have Doppler effects with sound and the change in the frequency of sound due to the relative motion, we do have that effect with light. So even though the speed of light is constant regardless of the motion of the object that emitted it, the observed frequency is, you know, can undergo some sort of Doppler shifting. So specifically the rocket ship that's moving, if you're looking at the headlight as it comes towards you, the Doppler shift would increase the frequency since it's coming towards you.
Moving at all.
And so you see, you know, blue and purple frequency there when it really was emitting a red frequency. So two effects that we're going to focus on that arise from this experimental observation is two types of distortion. One distortion is a length contraction, and one distortion is a temporal dilation. So if you're observing an object that's in motion, you'll observe those lengths to be contracted, and if you make measurements of time intervals from a stationary point of reference, and you're making measurements from on a object that's moving, you'll measure time intervals that are longer. You'll measure time dilation and length contraction. And so this is also kind of outlined in the video for the rocket ship at rest. In 1 second, light will travel this amount of distance.
For 1 of our seconds, sure enough, both beams will have traveled a light
but
second.
for the ship
the
that's
crew of the
moving
ship measures light speed
instead
to be
of
the same as
light
us. How does
travels,
that make sense?
the distance light travels in 1 second is not that full 299 million meters. Instead, it's this shorter distance, a contracted length distance.
They wouldn't agree that a second has passed yet either, because of course to
and
us, time
in
is
addition
slower
to
for them.
that
They count
contracted
1 second
length
finishing later
distance,
than we do, at which point
time
their
is
light
also
has indeed
dilated,
passed
so
one
it
of their
takes
light seconds
longer,
from them. Observers will often
so it would take longer for light to be able to travel that distance. So for the rocket ship at rest, it takes 1 second for light to travel this distance, but for the rocket ship that's moving, for light to travel that same amount of distance, you either have to take into account that the length has been contracted or time has been dilated. If the length has been contracted, you'll see
and they wouldn't agree that a second has passed
a different
yet either,
distance
because of course to us
that light
time
travels.
is slower for them. They count second to be is
you'll see
No
a
problem.
different
You see,
distance that
what
light
they
travels.
measure a light
Or
second
if
to
you take into
be
account that
is
time has been
shorter than
dilated,
what we
then
measure.
for that
And
same
they
interval
wouldn't
of
agree that a
time,
second has
it would actually
passed
take
yet either,
longer.
because,
So
of
if
course, to
you
us,
take
time
into
is
account
slower
that
for them.
time is
They
dilated
count 1
and
second
allow
finishing later
the
than
rocket
we
ship
do.
to travel for longer, since that would be the same time interval as experienced by the people in the rocket ship at rest, then for a longer period of time, light would cover that same amount of distance. So you have two effects there that are in regards to the effects of this constancy of the speed of light. One is that the length is contracted, and so that's this equation right here. And so it's a very straightforward equation. The zero subscript indicates the length that you would measure if everything is at rest. Whereas then if you multiply it by this square root term, L with no subscript is the length that you would measure if you're measuring that same object, and the object is moving relative to you at some velocity v. So square root of 1 minus the ratio of the velocity and speed of light quantity squared. And so this expression will always give a length that is smaller than L naught. So the observed length will be contracted. It will be shorter if you're making a measurement of a length that's moving at a velocity relative to you. So L naught is referred to as the proper length. The proper length because if you were in the reference frame with that rocket ship or whatever thing that has a given length and that's moving, you would measure a length that is shorter than that. But what is really there, because if you are in the reference frame, even if you're moving at a very high rate of speed, you would just measure the length as being its proper length. You would measure the length as if you were just completely stationary. But if measurements are being made, with a relative velocity, so either if a rocket ship is moving very quickly, if you were in the rocket ship, you would measure its proper length because you would just assume that you're not moving at all. But if measurements are made with respect to a reference frame that's not moving relative to that rocket ship, then you would measure a contracted length, and you'd use this equation to calculate to what degree the length has been contracted. And same idea here with time dilation. Any time interval, so 1 second or any amount of time interval is dilated. So that means that if you're on a rocket ship and the rocket ship is moving very quickly, you'll measure time completely normally because you are in the reference frame where if you're moving at a constant velocity, your physics is the same as if you were not moving at all. And so you would not experience any time dilation because you are not moving relative to the rocket ship. The rocket ship maybe is moving relative to, say, the Earth, but if you are in the rocket ship, you are in that reference frame that's already moving, so you would experience the physics of moving at high speed as if you were not moving at all. And so in the rocket ship, a certain time interval would be measured as the proper time interval. It would just be measured as if everything was completely normal and you weren't moving at all. But if you were on Earth measuring the time interval on the rocket ship, you would measure a time interval that's longer than what it would be experienced as if you were on that rocket ship. So the time has been dilated. You would measure 1 second going by on the rocket ship, you would measure as 3, 4, 5, whatever. You would see that time has been dilated, meaning that 1 second would take longer than 1 second on the rocket ship would take longer than 1 second if you were on the Earth not moving relative to that rocket ship. And so again, that equation takes into account the square root expression, 1 minus the ratio of the velocity and the speed of light quantity squared. And so those are, the two expressions that are pretty straightforward that get to the mathematical core of, of what's going on, is that there's distortions due to relative motion, and due to the speed of light being constant regardless of the underlying motion, these equations arise. The temporal distortions and the spatial dimensions arise because of relative motion and because of the constancy of the speed of light. So these distortions would never arise if you were just within your own reference frame. These distortions are only measured if you are making measurements with respect to something else that is moving, or perhaps you're moving and the other thing is stationary, but the equations would be the exact same. If you're moving and the other object is stationary, the mathematics will be identical as if you are stationary and actually it's the other object that's moving. So that's kind of the one idea of the principle of relativity, is that even if you're moving, your physics is going to be exactly the same as if you're completely stationary. Another link in the lecture outline is actually a game, and it was produced by MIT, and it's hosted on their website, and it allows you to visualize some of the distortions that occur because the speed of light is finite. Specifically, you will be able to observe spatial distortions and the Doppler shifting of the frequency of light. So if you follow the link, download the most recent version. The 2013 version is on there now. Download it, agree. Go through all the steps to get it downloaded, installed, and then you should be able to run it. And so yeah, you can. There is like a short introduction, a few short introduction slides. I'll just skip through them, but basically it's introducing the fact that the speed of light is finite, and so there's going to be effects because the speed of light is finite. And in this game, you will go around collecting orbs, and by collecting orbs, you will reduce the absolute speed of light, meaning that as you collect more and more of these orbs, the effects of a finite speed of light will become more and more apparent. So you use AWSD to move, you use your mouse to look around, and so you'll go around and collecting all the orbs, and so it'll, initially you won't visualize, you won't see too many of the effects of the speed of light. There's also sort of like an icing effect in the game where you won't stop and start. You can't stop immediately. It kind of takes a little bit of time to stop. So that it's kind of weird, but yeah. So after a while, you will be able to definitely observe the Doppler shifting of light. So if you're just completely stationary, as I am now, you'll see everything with a certain color. But if I move forward, what you'll observe is that the colors of light are shifted up. So any color that you observe just normally, if you start moving, you'll see those colors shifted towards the blue or purple end of the spectrum because the speed of light is constant. But you are actually now moving towards the light that's coming at you, and so you'll see the frequency be shifted. And you have the opposite effect if you move backwards. If you move backwards, you'll see light shifted towards the yellow or red end of the spectrum, and so that's an effect of the finite speed of light that we don't see in every day. You also see some distortion if you move left or right. You can't really see it right now, but if you collect, if you get up to above 50 orbs or so, you'll be able to see some of the spatial distortions that arise from the finite speed of light, that are kind of related to the length contraction. But they and so there's spatial distortions and there's temporal distortions, and so that game is just available to kind of highlight some of those distortions that that are observed due to the finite speed of light. So it's just spatial distortions and the frequency distortions specifically in that game. That you don't really have any way to measure time intervals while you're moving. So it's just spatial and frequency distortions. And so that's special relativity. So anything that refers to is in regards to light and constant velocity would fall under special relativity. If you are accelerating, those conditions would be described by general relativity. So specifically, general relativity is a description of gravity with kind of this relativity paradigm in mind. Specifically, if you are free falling under gravity, you can apply the principle of relativity to when you are free falling under the influence of gravity. Specifically, I guess when the principle of relativity, when applied in the general relativity context, the principle of relativity applied to reference frames that are accelerating, which is what would be happening if you were free falling under gravity. That's called the equivalence principle. And in another video that's illustrated by Brian Greene dropping a water bottle, an Nalgene water bottle
The great
that
enemy of
has
writing
holes in it.
isn't your own lack of
And
talent.
so you can,
it's
if
being
you're
interrupted.
falling in free fall
have
under
to do
the
anything?
influence of gravity,
No, it's very simple, right? So all we have here,
you can treat that reference frame as if you were, again, if you were
is
just
a
completely
bottle
at
of
rest.
water that has holes
So
in
the
it,
idea
right?
here
So of course the water is
is
spraying.
that the bottle is full of water, and there's holes drilled in the sides, and so gravity is pulling on the water
out of the holes
and
because
the
gravity
water
is pulling on
flowing
the water,
out
right?
the bottom.
But if Einstein is
But,
right, if I drop
if
this
you drop
bottle,
the
the water will no
Nalgene
longer
bottle,
feel gravity, so the water should stop
what
spraying
you'll
out.
find
Let's
is
see
that
it.
the water
3,
stops
2,
flowing
1.
and there is no gravity. So the moment that you drop it, that entire bottle is now in free fall, and the water is no longer coming out of the sides. And so if you're if you're in this accelerative free fall, you can actually treat this reference frame as if you are not experiencing gravity whatsoever. So that's sort of the principle of relativity applied to gravity, where if you're in gravitational free fall, you are accelerating. So you're not at a constant velocity, your velocity is changing, but despite that, you can still apply the principle of relativity, the equivalence principle in this context, where it's almost as if there's no force of gravity acting on you whatsoever. So the idea there is if you're accelerating in free fall due to the effect of gravity, you will experience the physics as though there is no gravity whatsoever, as you can see, and that's actually illustrated by there because there's no water coming out of the Nalgene bottle.
Now, did Einstein Did Einstein have any theories about who's going to clean that up right now? Okay, so he.
And so, similar to how you have spatial and temporal distortions due to the finite speed of light, applying the principle of relativity to the finite speed of light, if you apply the equivalence principle now to gravity, you'll also have a similar effect where you have spatial and temporal distortions, where if you have a gravitational source, so a sun, a planet, anything that has a gravitational field, that gravitational object, if you were to calculate, say, the gravitational force in empty space, well, you'd only have the source and empty space. So Newton's law of gravity requires two masses for a force to be exerted. So the gravitational effect of a large star or a large planet in empty space will be zero. There'll be zero force there. But if you apply the equivalence principle to its mathematical end, you can show that a planet or a massive object will have an effect even in empty space. So Newton's description of gravity with forces says that gravity has no effect in empty space. But now applying relativity to this interpretation of gravity, where if you're falling under gravity, your physics is actually the same as if you were not falling under gravity at all, you can take that first principle to its mathematical conclusion and infer that gravity does have an effect even on empty space. It distorts space and time due to this relative motion, and that distortion of space and time is what we mean when scientists talk about warped space-time. Gravity warps space-time, and then objects that pass through that warped space-time will experience the effects of gravity. So if you were to pass through truly empty space, and there was no planet, there was no gravitational effects around whatsoever, you would just go in a straight line. There would be no effects due to gravity. But if you were passing nearby a planet or a star, you would not go in a straight line. You would be affected gravitationally. You would be attracted to that mass. And the reason why, in the context of general relativity, is because from your frame of reference, you're going to assume, that you're in an accelerative free fall, and your physics is the same as if you were not accelerating it at all. Your physics would be the same as if there was no gravity. But what you observe is that you're getting attracted to the object. You're getting closer and closer to the object. You're getting pulled towards that object, and the reason that is then given for that attraction is that that there's an attraction between masses. If the planet or the star wasn't there, there'd be no gravitational attraction, and you just move in a straight line. So the reason that you can supply for why you are no longer going in a straight line is because the mass has warped space and time there. And it's warped space and time in such a way so that you don't go in a straight line, but you go in a line that brings you closer to the planet. You're attracted to the planet. And of course, for all normal everyday activities, we don't have to understand that attraction as being a warping in space of space and time. That's just more complicated than what we really need to understand gravity at the everyday level. You can simplify it as simply being, well, there's a gravitational force that's pulling me towards that mass. But it's been found, through experiments and testing, that the idea of a gravitational force, some pulling action that occurs between two masses, is not a force. It's approximately a force, and it's good to understand gravity as a force for everyday types of knowledge, because that's all we really need. But to try to understand it as accurately and as fundamentally as possible, we have to describe gravity as an effect that results from this idea of relativity. As if you're in gravitational freefall, your physics is the same as if you were just completely at rest. But the fact that you are moving towards the object that you're accelerating under in free fall, you attribute that to the gravitational effect, the effect that gravity distorts lengths and times in such a way that causes an attraction to arise, an attraction that can be approximated very well as simply being a force. And so there's another demo in this video, and it's a demo that you've probably seen before, where you have an elastic sheet and you place a mass on this elastic sheet, and it's supposed to illustrate the distortion of space.
He says if there's no matter, no energy, then
due to
space
gravity,
is flat, right? Which would mean
but in
that
many
if you roll
explanations,
something, say a planet is moving through space, it goes on a straight line.
The explanation is circular. If the explanation isn't completely
but now
explained,
the sun.
It's very circular, because if you place a heavy mass that distorts the sheet, the reason why the sheet is distorted is because of gravity. So gravity causes gravity in a sense. And so that explanation is incomplete. If you just say, oh, well, the mass in the center bends the elastic sheet, and then objects that now travel on that elastic sheet are attracted to that mass.
It makes like a well.
So in a sense,
because now we
gravity, trying to explain gravity
and we set
with
it in motion,
gravity. And so it's not really illuminative by explaining it in that matter. But what really matters is this overhead shot. Because when the elastic sheet is flat, that would be the case of being completely at rest. There's no gravity, and you just travel in a straight line. But now with this overhead shot, where you can see that space-time is distorted, the object that's moving in a circular orbital path around that central object, it still assumes that that space is flat. So, if this ball here is assuming that space is flat, it's noting, well, okay, space is flat, but I am not going in a straight line. And so the reason why it's not going in a straight line is that I can infer, well, the reason why it's not going in a straight line is because there's been a distortion of space in such a way that causes me to not go in a straight line, but causes me to go in this orbital path around the central object that has mass. And so that orbiting ball then would attribute its motion, which would attribute its non-motion of not going in a straight line. It would attribute its accelerative motion to the effects of gravity, where you have an object that has mass, and the mass has distorted space in such a way so that it's causing this attraction.
And that is,
and it's this overhead view
is how gravity works, right?
Is what really allows you to understand that. Because if you don't understand that the ball that's rolling, it still has to think that it's in flat space. If the ball doesn't know that it's in curved space, it's attributing its orbital motion to the effect that the central mass has on the distortion of space around it. And so that's
all of these planets,
how you can move from
objects,
a stationary reference frame, where
so this, according to Einstein,
the physics would be the same as if you're under the influence of gravity, although if you're under the influence of gravity, your motion is not the same as if you were just going in a straight line, not under the influence of gravity, because the underlying space is distorted in such a way that causes an attraction.
Actually works.
so you do part of this overhead view then assumes that you are makes the connection that the physics of a stationary reference frame has to correspond to the physics of an accelerating reference frame, because if you really are accelerating due to gravity, but you assume that you're moving at a constant speed, the differences that you'll measure can then be attributed to the effects of gravity on the distortion of space, which again are very similar to simply an attractive force, but fundamentally, in the most accurate way to describe it, it's not a force, it's a distortion of space-time, and so the difference there is that if you assume gravity is a force, that mass has no effect on empty space, but if you take the principle of relativity, the equivalence principle, to its mathematical conclusion, you'll find that that the effect of gravity does have an effect on empty space. So even if you have a central mass and no mass around it, there will still be an effect there. Whereas if you describe gravity as a force, there would be no gravitational effect. But with this new interpretation, gravity would always have an effect, even on empty space. Okay, so that's all I'll cover with respect to relativity. It's a very, being able to grasp the concepts, I think, are more important as a first step than being able to grasp the mathematics, because even though normally in physics, knowing the mathematics illuminates the concepts, and knowing the concepts illuminates the mathematics, I think in relativity, it's such an abstract topic that it's better to just focus on the concept until you understand it so well that the equations just follow naturally from the concepts. I don't think it's easy at all to go from the mathematics to the concepts when in relativity. I think you really have to have a good mental imaging of what's going on before you can really grasp why the mathematics are the way that they are. And so yeah, we'll only have two equations with relativity that only apply to special relativity. So I only talked about general relativity at the conceptual level. We'll only have questions in regards to special relativity, so distortions that arise when you're moving at a constant velocity, distortions of space and time. Alright, so I'd also like to talk briefly about quantum mechanics. So what I'll talk about specifically is just the union of understanding light as a wave and a particle. Specifically, we'll be learning about the photoelectric effect. That's the material that we'll focus on with respect to quantum mechanics. But I'll try to describe quantum mechanics conceptually too, in the same way that I described relativity conceptually, because it's the same story with quantum mechanics, where it's probably more important as a first step to understand the concept behind quantum mechanics rather than trying to understand the mathematics first and then inferring the conceptual implications from the mathematics, because the mathematics are the mathematics, it's not too bad by themselves, but trying to infer conceptual ideas from mathematics in this context, I don't think it's the best way to go. Right, so what we'll really focus on is what's called the photoelectric effect. So we've treated light as a wave. We've in the double slit experiment, we've seen specifically how light acts like a wave. When we studied lenses and mirrors, it was clear that we could treat light as a ray, as a particle of light, and then it simply went in straight lines. It either reflected or refracted. And so we've had two very successful means to describe light as both a particle and a wave. And so we'll be able to combine them with a very simple equation, in fact. But first of all, the sort of mental picture that you can have with a photon is the picture here, where a photon has both wave and particle qualities. A photon is a vibration of the electric field that you can see here, but that vibration takes up a finite amount of space. The space is occurring in this x dimension, and the vibration occurs over a finite dimension. So a photon has wave properties because it's an oscillation of the electric field, but it also acts like a particle in the sense that this wave disturbance happens over a very finite area. And so that's the mental picture you can have of a photon, and how light can have this wave-particle duality where it's both a particle and a wave. Most fundamentally, I would describe it as being a wave because it is the vibration of the electric field, but it is a contained vibration, in space. And so because of that sort of contained wave disturbance, it acts like a particle as it travels through space. And the key equation here is this first equation, which tells you the energy of just a specific photon given the frequency of light. And h is a constant, Planck's constant, and so you can look, so you can reference that. I don't have it here, but it's a constant that's available in the textbook. And so this simple equation is able to relate the wave and particle properties of light, because on the right hand side you have the frequency of a wave, and on the left hand side you have the energy of an individual particle, the photon. And so this simple equation concisely marries those two descriptions of light. Light as a wave, light as a particle. So whatever frequency the light has, that corresponds to the energy of a single photon, the energy of a single disturbance that has a corresponding frequency when you have an ensemble of a whole lot of photons. And the experiment where this was really brought out was an experiment associated with the photoelectric effect. And in this experiment, fairly simple experiment, what was measured is that light photons would collide with electrons, and those photons would give their individual energy to individual electrons, and those electrons would have energy, and that energy was measured as current. So another link in the lecture outline is a link for an online physics applet simulator, where the photoelectric effect is where you have information on the photoelectric effect. So you have incoming light. That's where our photons are. The incoming light that shines on just a plate of metal. In this case, we have sodium, but we could also change it to zinc, copper, platinum, calcium, or some mystery material. So light shines on the material, and this is sort of a vacuum tube in between, so the electrons can move from one plate to the next and generate current. So light shines on the metal, electrons are emitted, and those moving electrons are measured in terms of current. And you can also have a battery here, and this battery will make the current. It'll either, once the electrons are freed from the metal due to the incoming photons knocking them out of the metal, this battery will either assist the electrons, driving more current, or this battery will oppose the electrons, making it harder for current to flow, as we'll see. So the idea here is that light has energy. We know light is a wave, and so if we change the intensity of the light, so if we just shut the light off, there's no energy on the metal plate, and there's no way that the electrons will have energy to escape their underlying material and travel to the other plate to drive a current. But if we increase the intensity of the light, we're increasing the energy impingent on this metal surface. So if we increase the energy, it seems like we should be able to add enough energy until electrons finally shoot out of the material and generate current. But even at maximum intensity, at this certain frequency, at maximum intensity, we have no electrons being emitted. So we have a lot of energy, hitting the electrons, but for some reason, no electrons are being emitted. If we turn the intensity way, way down, so we have very little light energy actually hitting it, but if we change the frequency of light, if we increase the frequency of light by just a little bit, what we'll find is that electrons now are being emitted. So even though we have very little overall energy, but we've increased the frequency to a certain extent. So even if we have very low intensity, we have higher frequency, meaning that the frequency of light is increased, but the overall energy supplied is very, very low. So if we have high frequency but low intensity, we're able to observe these electrons being emitted by the metal. But if we decrease the frequency or increase the wavelength, even if we ramp up, if we have a long enough wavelength, a low enough frequency, even if we increase the intensity to its maximum amount, there's no way we're going to be able to get electrons emitted from the metal, which is strange because we still have plenty of energy available here. If we crank up the intensity, we have more energy, more total energy, but the energy in a single photon will not be enough to knock an electron loose. The only way to knock an electron loose is to have a particle of light, a photon, that has enough individual energy to knock the photons loose, and the electrons that are then knocked loose travel to the other end, which can be measured as currents. Yeah, so if you have high enough frequency, you'll be able to measure this current. And so that's partially implicated in this equation, but it's also we're able to understand this in terms of more everyday type of example. If you think about a pool of water, in this case, from the wave perspective, if you have water in a pool and you'd like the water to escape the lip of the pool, if you add energy as waves, you can always add enough. If you add enough energy, you'll be able to generate water waves that eventually have enough energy so that they go over the lip of the pool. And so that would be sort of a wave perspective. But for a particle perspective, you can make that happen by, if you just have a single pebble, throw it in the pool, and that single pebble can cause a drop of water to escape the pool, because that one pebble gives all of its energy to that one drop of water, whereas giving energy in the form of waves would distribute its energy equally. And so that's the conclusion that was inferred by this photoelectric experiment, is that even though you have light coming in as a wave, the only way you can cause the electrons to escape is if the individual particles of light have enough energy individually as individual particles to give enough energy to individual electrons, which can then escape the metal. So there's so this is analyzed with energy, and we'll analyze it with energy. Specifically, you have energy in the form of photons. So energy in the form of photons hits the metal plate, and that energy is converted to the motion of electrons. We also have this battery here, which comes into play because if you you can either have the battery of the voltage oriented to increase the current, or you can or to you can have the battery oriented to increase the speed of the electrons as they're emitted from the metal, or you can have the battery facing the opposite way, where they'll actually repel the electrons that are emitted by the metal due to the incoming light. And so at certain voltages, you'll have just enough energy to reach the plate, and at other voltages, you'll just you'll increase the velocity of the electrons as they reach this opposite plate. So again, that's analyzed with energy. And so I have 3 steps here: the energy analysis, the conservation of energy. So the initial energy is equal to the final energy. The initial energy is the energy of the incoming light, the energy of a single photon. That energy is converted into the energy associated with the electron. That energy is converted into 3 parts: a kinetic energy of the electron, the potential energy of the electron, and the work done to pull the electron out of the metal. And so this energy analysis, says how the energy is conserved. The energy of a single photon converts to, it first has to pull the electron out of the metal, which is, and so that value will just be a constant, a material-dependent constant that is constant for a given material. And then if the photon has extra energy, it's going to give the electron extra velocity, extra kinetic energy. And then you have a third term, a potential energy, meaning that if you have a velocity, or if you have a voltage that's a back voltage or a stopping voltage. Let me just increase this here. So if you have a battery that's discouraging electrons to cross the plates, that would be a stopping voltage, and the electrons that do reach this opposite plate, that's the final state. The initial state is the photons, the final state is this right plate. This voltage would be the stopping voltage, and that would be a potential energy, because the electrons that absorb the photon energy, that energy is converted to kinetic energy, but also the potential energy, because they've overcome the potential of the battery. And of course there's the work energy, the energy to actually pull the electrons out of the plate in the first place. And we'll also use, when we use this equation, we'll use units of electron volt, which is a unit of energy. Just like joule is a unit of energy, the electron volt is a different unit of energy, and so there's a simple unit conversion between joules and electron volts. Just as you can convert between meters and feet, you can convert between joules and electron volts. But a lot of times it's simpler. But yeah, so for any given equation, an equation will work regardless of your choice of units. But this particular equation does use units of electron volts. That's why potential energy is just a voltage, and so each one of these terms here has to be in units of electron volts rather than in units of joules. But yeah, it's just a unit conversion since they are both units of energy, just two different units. And so I definitely want to go over the questions, for the photoelectric effect. For relativity, the equations are pretty much going to be plug and chug. They'll be pretty straightforward. So these first two questions, it's really just plug and chug, where you have a proper length and a relative velocity. You can measure the associated length contraction. Same with time dilation. If you're on a spaceship that's moving, you of course would experience that time just completely normally. But if someone on Earth is measuring your time intervals, they would measure your time intervals passing slower. And so the time interval on the spaceship would be 10 times slower, or 1/10 whatever is measured on Earth. So so you can just plug those values in and quickly determine what the speed of the spaceship has to be in order for the person on Earth to measure a dilated time interval by a factor of 10. So I don't think there's going to be any problems with the mathematics of what we're going to be doing in relativity. It's very straightforward, pretty much plug and chug, since that's all we have time for. Maybe a little bit more attention will be needed for the photoelectric effect, but again, it's just that one equation. So in this first question, number 67, we have a certain metal, aluminum. Light hits that aluminum. It emits the electrons, sometimes called a photoelectron. So how much energy, the work function, so that's how much energy does it take to actually extract the electron from the aluminum. Yeah, so for this question, we set up our conservation of energy, which is just the energy of a photon on the left-hand side. That energy converts to the kinetic energy of the electron, plus maybe a voltage that it has to overcome, the stopping voltage, and then the work function, the amount of energy it actually takes to extract the electron from the metal. And so in this one, we're just considering, how much energy does a photon have to extract it from the metal. And so the electron comes out with zero velocity. It doesn't have to overcome any voltage. And so the energy of a photon, all that energy does is just pull the electron out of the metal. It doesn't give it any additional energy. So we use the constant h, Planck's constant, times the frequency of the light, and we'll use that to compute the work function, how much energy it takes to pull an electron out of the metal. Planck's constant is 4.14 times 10 to the negative 15th electron volt times seconds. So that's just a constant. And the frequency of light is the speed of light divided by its wavelength. And when you multiply that out, you'll end up with units of electron volts. And so electron volts is a unit of energy. You could convert this work function to joules, but obviously it's a very small value. Since we're talking about just the energy of pulling one electron out of a metal, it's going to be a very small amount of energy, and so since it's a small number, it's practice to convert to electron volts, because then you don't have to be writing 10 to the negative 18th joules and whatnot all the time. You can work with just sort of more normal looking numbers, but they represent very small energies. Next, in this next question, so again we're applying this conservation of energy equation, where this time we have the energy of a photon, and it's converts to, and that electron is given velocity. Well, it's pulled out of the plate, so there's energy associated with the work function of the work of pulling it out, but then it's also given additional energy in the form of velocity, kinetic energy. So again, but it doesn't have to overcome any stopping voltage, so that voltage is 0. So the Planck's constant, 4.14 times 10 to the negative 15th electron volts times seconds, times the frequency of light, equals the kinetic energy plus the energy of the work function. You solve for the kinetic energy. Kinetic energy equals, the kinetic energy of the electron with the given information is 10.795 electron volts. Now, if you try to solve for the velocity, because kinetic energy equals 1/2 mv squared, 1/2 mv squared has units of joules if you're using kilograms for mass and meters per second for velocity. So we can convert electron volts to joules in order so that we can use the 1/2 mv squared equation. So we have an energy in electron volts, we convert that to joules, and the unit conversion between joules and electron volts is 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. So yeah, 1 electron volt is a very tiny amount of joule, and so when we deal with very small energies, specifically energies are just single electrons or single particles, we use units of electron volts, because then we don't have to write these tiny numbers all the time. We can just write the amount of energy in electron volts. So we can convert to joules by multiplying by a conversion factor the conversion of units from joules to, from electron volts to joules. And when you convert that to joules, you get 1.7272 times 10 to the negative 18th joules. So yeah, very small number. That equals 1/2 mv squared. You solve for velocity, and so you can solve for the velocity there. So that's the additional velocity an electron would have if an electron within a metal is hit by a photon of a given wavelength, and that energy pulls the electron out of the metal and it accelerates to a certain speed, and we've determined what that final speed is. Okay, last question. 3 parts. So again, I mean, it's the same setup, the same photoelectric setup, where we have light hitting a plate, electrons are pulled out of the plate. Yeah, so we're given some information. We're given the initial energy because we're given the energy of the photons, because we know the wavelength. So if you know the wavelength, you automatically know the energy of a single photon. And there's 3 parts. And so the 3 parts just have different conditions, but in each part we'll use the conservation of energy equation. So in part A, we'll apply the conservation of energy equation, and in part A, the photon that has the wavelength 600 nanometers, it pulls the electron out of the metal. It gives the electron a kinetic energy a certain amount of energy given in electron volts. That's this number here. And there's no stopping voltage for part A. So with that information, you can determine how much energy it took to pull the electron out of the metal, because you know the energy of the photon, you know the kinetic energy that it has after the electron is pulled out. That's just given by the problem. There's no stopping voltage, and you're solving for the work function capital W naught. Solve for the work, so it equals the difference in the energy of a photon and the kinetic energy. Plug those things in, you get the work function, how much energy it takes to take an electron out of the metal. And for part B, it asks for the cutoff frequency of the surface. And so what's the minimum frequency you need in order to pull out an electron? So for part A, we had additional kinetic energy, the 0.17 electron volts. But for part B, it asks, we could use a longer wavelength light, lower frequency, and if we use that lower frequency, each photon will have less energy, and so the kinetic energy will be correspondingly smaller for that wavelength of light. And so you can still pull electrons out, they just won't have as much kinetic energy. And so the cutoff frequency will be when the kinetic energy, you have no kinetic energy with the photons, no kinetic energy of the electrons. The photons have just enough energy to pull the electrons out, and then they'll just sort of be floating in space. They'll be out of the metal, but they'll have no additional kinetic energy, and the stopping voltage is still 0. So you equate the energy of a photon to the work function, solve for the frequency, and you can solve for the frequency. And if you convert that to a wavelength, I'm just curious, I'm surprised I didn't put it on there, but if you convert that to a frequency, you'd get 652 nanometers. So if you have a shorter wavelength, higher frequency, more energy, the electrons get pulled out and they have an additional amount of kinetic energy expressed in electron volts. But if you used a longer wavelength, so 652 nanometers, 652 nanometers will be longer wavelength, lower frequency, and less energy per photon, and that's the cutoff frequency, where you have to have at least that amount of energy per photon to simply pull the electron out of the metal. If you have a frequency of light any less than that, you could have the most intense light in the world. So if you had instead 700 nanometer wavelength light, that wavelength would be too short to pull electrons out of the surface. So you could have all of the 700 nanometer light in the world focused on this plate, but it would not be enough energy to extract the electrons because the individual photons don't have enough energy. Finally, part C, it's a question on the stopping potential. So if you have even shorter wavelength light, that shorter wavelength light has higher frequency, so it has higher energy per photon, and so therefore that will have more than enough energy to pull the electron out of the surface. It'll give it additional kinetic energy, but then if you apply a stopping voltage, that kinetic energy will be essentially canceled out by the voltage in such a way so that the energy, the kinetic energy, the voltage slows down the kinetic energy and gets stored as potential energy. So you solve for that stopping voltage. So you have the energy of the photon, which is your initial energy. You have the energy it took to pull the energy out of the metal, and then the kinetic energy is going to be 0, because the kinetic energy has to be 0, because that's the definition of the stopping voltage, is that if the incoming photon has more than enough energy to pull the electron out and accelerate it to a certain velocity, then the voltage, the opposing or stopping voltage, will actually slow that electron back down, and it'll slow it back down to a velocity of 0, kinetic energy of 0. And so you've already solved for the work function, and so for this particular wavelength of light, you know the energy of a photon, and so you can quickly solve for the voltage. So the photoelectric effect is really as deep as we'll cover, will be as deep as we cover in quantum mechanics. If you'd like to go a little bit deeper, you can, you have the textbook. It's open for your use. It's again, I mean, we've really only scratched the surface of quantum mechanics, by thinking about the application of photons and their properties of waves and particles at the same time. But the overarching conceptual subject of quantum mechanics, it goes a lot more deeper than that. In fact, really, for the core subject of quantum mechanics, the photoelectric effect is, related to quantized particles. Photons are quantized particles of the electromagnetic field, but we really haven't even scratched the surface of the mathematics associated with quantum mechanics. And I'll try to talk about it conceptually here. I mean, just just because it is interesting. Quantum mechanics. So again, quantum mechanics. It does. Have those two components of treating particles simultaneously as a particle and a wave, and it does that by assuming these sort of wave packets. The same picture we had for a photon is that you have wave disturbances that exist in a finite space, and by doing that, you have a particle that has properties of both particle and a wave. But conceptually, quantum mechanics describes the probabilities of finding a particle. The wave part that's described by quantum mechanics is not the wave vibration of the electromagnetic field. So the picture of the photon is a wave vibration in the electromagnetic field, but the formal topic of quantum mechanics, it describes waves that are not waves in the electromagnetic medium. It describes waves that are probability waves. In particular, if you've ever heard of the Schrödinger equation, and it's in this chapter, right. Yeah, so the Schrödinger equation, I mean, it looks complicated, but for conceptual purposes, we'll just, look at the derivatives, because we do have partial derivatives, but you have a first derivative in time, you have a second derivative in space, and you have the two functions themselves. So just if you looked at this mathematically, just put aside what the functions u and capital psi represent physically as a mathematical equation. This will describe a function that's exponential. If you have a differential equation that's in terms of a function, its first derivative and its second derivative, those are typically solved with some sort of exponential function, because if you take the first derivative of a function, you get the function back. If you take the second derivative of an exponential function, you still have that same function. And so the Schrödinger equation is designed so that it outputs some type of exponential equation. And the Schrödinger equation includes a complex variable. It includes the variable I, and if you've ever studied complex mathematics, complex particularly meaning imaginary and real parts of a value, the whole point of complex mathematics is to describe periodic motions, wave motions, in terms of exponential functions. And I'm not going to get into the mathematics of that because I'll reserve that for another class. I'll see if I can find it in this chapter, but the idea is that using the complex mathematics, you can express waves as in terms of exponentials. And so these two lines kind of express what I'm saying. This capital psi, which is a function that does appear in the Schrodinger equation, is in terms of an exponential function that has a complex exponential. And the reason why this is done is because this complex exponential can be written in terms of, because a natural logarithm with a complex exponent is actually describing a periodic function. It's just a different mathematical form of describing a cosine or a sine. So anytime you see a natural logarithm with an exponential function, its whole purpose is to describe sines and cosines with a function that aren't sine or cosine. An imaginary number is exactly that. It's imaginary. It does not exist. So you always will always have a for any number that has an imaginary component, you're only ever considering the real component of a complex number, because if it's imaginary, it literally does not exist. And so if you have a complex value, especially when it relates to physics, you're really only the real part is the part of the function that you're gonna end up using and will correspond to some real measurement. Right. So we have the Schrodinger equation. We have the solution to the Schrodinger equation, which is in terms of complex exponentials, which are really a description of a periodic wave, a cosine or a sine, and that those cosines or sines describe this capital psi, which is called the wave function. And so this wave function tells you the probability of finding a particle. And it's in some of these earlier equations. The probability of finding a particle is equal to the square of the wave function capital psi. So you have Schrodinger's equation, you have the solution to the Schrodinger's equation, and you use the solution to the Schrodinger equation to calculate the probability of finding a particle in a given location. This wave function, well, it's a wave, and so waves can interfere constructively or destructively, and so it has wave particles, but when you actually make a measurement at a particular position, you will find a particle. Just a minute. Yes. All right. So we have the Schrodinger equation. We have the solution to the Schrodinger equation, which is a wave, and it's called the wave function. And with that solution, the wave function calculates a probability of finding a particle. And yeah, so you can see a couple example wave functions. They're definitely waves. And they have particle properties in the sense that they are contained. They're waves that are contained in space. And so they have wave and particle characteristics. and you use that wave function to calculate probabilities. So fundamentally, quantum mechanics is a statistical subject. It's a subject that describes statistically where will you find a particle at when you make a measurement at a point in time. Just looking for another good picture of a wave function. Yeah, I mean, if you look at this one, so for like the energy levels in an atom, the n equals 1 state or 2, n equals 2 or 3, you use Schrodinger's equation to solve for a some sort of wave function, and then that wave function will tell you the probability of finding a particle at a particular point. So you would most likely find a particle here, here, or here, since they have the greatest amplitudes. That's where your greatest wave vibrations are occurring. But I don't want to get into more detail other than that. Yeah, something like this, where if the wave function, which is the solution to the Schrodinger equation, the probability is proportional to the square of the wave function, and so again, quantum mechanics tells you the probability of finding a particle. So you'd most likely find a particle there, there, or there, but you'd rarely find a particle there. And again, something like this, you have equal probability of finding particles in all different locations. Once you realize quantum mechanics is a statistical subject, that's kind of where the Schrodinger's cat paradox arises. Because before you make the measurement, there's a probability of finding a particle in a certain location, but before you make the measurement, the way quantum mechanics is understood is that before you make the measurement, multiple waves are interfering constructively and destructively, meaning that the one measurement that you're making is a combination of multiple wave states of a particle, because any particle is not just a particle; it's a wave. And a wave has that property of interfering with itself or other waves. And so if you have a statistical wave describing a particle, that's once you make the measurement, a definite state is defined, but before you make the measurement, there is no definite state of the particle, definite state of the object. The whatever you're measuring, before you measure it, exists not as a single state to be measured. It exists as a multitude of states that are interfering with itself. And you can illustrate that with just a very simple example. If you flip a coin, you have a 50% chance of getting heads. You have a 50% chance of getting tails. So before you flip the coin, if you describe your expected flip with quantum mechanics, it would probably say something like the expected outcome is half heads, half tails. That doesn't mean anything. You can't have an outcome that's truly half heads and half tails. If you flip a coin, it can only be heads or tails. And so the idea then is applied to a cat, where if you have an action that's described quantum mechanically, specifically a radioactive decay, and that radioactive decay controls if a cat is alive or if it's dead, then when you describe if the cat is alive or dead, you have to describe it in terms of probability of, did that radioactive decay happen? And when you describe it probabilistically, it's described, well, before you make the measurements of did the radioactive decay happen, quantum mechanically, it's a superposition of a probability wave describing that the radioactive decay did happen and it didn't happen. So if if the real state of a system is a superposition of two possible outcomes of the system, how can a cat be alive and dead at the same time? And so this superposition of probability waves is at the heart of quantum mechanics, and its weirdness is illustrated with the example of Schrodinger's cat. But yeah, conceptually, you have Schrodinger's equation. You have the solution to Schrodinger's equation, which gives you a probability function that looks like a wave, and then you use that probability wave to calculate the chances or the probability of finding a particle at a particular location at a particular point in time. And that's really the heart of quantum mechanics. But again, we only thought about quantum mechanics in the context of photons, specifically the photoelectric experiment or the photoelectric effect, where we can understand light as having wave properties and particle properties simultaneously. Okay, that's I think I'll wrap it up here. I've kind of given you just a conceptual background of special relativity, general relativity, and quantum mechanics, and some of the finer details of what I'd like you to be able to do computation-wise. I think it's going to be pretty straightforward. Obviously, relativity and quantum are very heavy subjects that we are just scratching the surface, but we're scratching the surface by trying to understand the concepts of these big ideas. And I think if you understand the concepts, that will help you immensely if you ever go on to the heavier mathematical machinery of relativity and quantum mechanics. I know that really doesn't apply to most of you, but just conceptually, I think most people agree that they're very mysterious subjects. They're not very well understood. They're very abstract. We don't have experience with them. So that's why I've emphasized the conceptual part of these topics rather than the mathematical machinery. That has its own fascinations, but I think in the context of general physics too, just treating these subjects conceptually really goes a long way. And if you're interested further, obviously the textbook's available. There's all sorts of resources available on the internet for deeper study, obviously. So I have the lecture outline posted, and the practice problems posted. I have the quiz posted. Quiz 9 will be the last quiz. We'll have a take-home exam on this material this weekend. So obviously, it's not going to be too in-depth. There might be some conceptual questions as well as calculation problems. Obviously, this last exam, since it covers the topics of relativity, quantum mechanics, those topics, we haven't developed fully calculation-wise, and so I think I will allow myself some freedom in how to write that exam for those two topics, specifically because it's a take-home exam, and so so whatever the question is, you'll have plenty of time and plenty of opportunity to make sure that you're solid on the concepts. Obviously, with interference and diffraction, we covered that a little bit in more greater detail, especially in the lab, and so that will be emphasized more heavily calculation-wise on the take-home exam. So yeah, we don't have really too much else other than that. I'll post a practice final exam by probably end of day tomorrow, end of the day Wednesday, and so you'll have an idea of what to expect on the final exam, because the final exam will be comprehensive, but it'll be on Canvas, and so there'll be more questions there will be 20 questions on Canvas, but there'll be shorter questions than the type of question that you've seen on our regular term exams. Because for the regular term exams, they've only composed, a subset of the entirety of Physics 2. Since the final is comprehensive, I'll have more questions, but each of those questions will be shorter. But I will prepare you for what kind of questions I'll ask by providing a practice exam, so you kind of know how to study and what you'll see on the exam, final exam. But yeah, so the semester is coming to a close. This will likely be the last video, because when I post the final exam, I'll just post it on Canvas, and any information I'll probably just post as an announcement. So this will likely be our last face-to-face meeting of this semester. So obviously, congratulations everyone for making it through Physics 2. It's a very tough subject, but it's very rewarding if you put in the time to learn it and really understand the concepts behind the equations. If you understand the if you just understand the equations, if you just understand the concepts, that has its own value. But if you understand both of them simultaneously, you really do understand physics. So I hope you got a lot out of this class. I hope you were able to learn some interesting stuff. It wasn't always easy, but the education that you get in college isn't always things that you'll need for the rest of your life. Sometimes the pleasure of education is just being able to understand the world at a deeper level than what you've understood otherwise. Sort of virtue is its own reward. Knowing, having that comfort of understanding the world is its own reward. And I hope I've opened up a little bit of the world from the perspective of a physicist. Okay, we just have the quiz, the take-home exam 4, and the final exam, and that will be everything we'll have. So if I don't see you again, have a great summer. Feel free to reach out, for if you need to communicate with me about anything. Best of luck, stay well, and I'll see you next time.